Good morning in Colombia and good afternoon in Europe. Welcome to this academic event. My name is Camilo Acevedo, and I will be guiding you throughout this PhD candidate's dissertation. The doctoral program in engineering at Universidad Pedagógica y Tecnológica de Colombia, Sogamoso, is very committed to our academic processes and our research oriented towards solving contextual problems. This doctoral program promotes three fundamental pillars. First, research as a route to find solutions to local problems with a global view. Second, self-management that encourages the autonomy and self-confidence of our students. And third, networking that promotes collaboration with the international community. We welcome you to the dissertation of the PhD proposal entitled Reliability Assessment of Deep Neural Networks Implemented in Parallelized Hardware Platforms, presented by student Luis Ariel Mesa under the supervision of Professor Wilson Javier Pérez Holguín and Ernesto Sánchez Sánchez. This dissertation has been scheduled by the academic coordinator, Professor Germán Antonio Fernández, as well as Professor Luis Ángel Lara González, who is the Dean of Sogamoso faculty. We also welcome the reviewers of Luis Ariel's proposal, Professor Alberto Bocio, who is with École Centrale de Université de Lyon Institute of Nanotechnology as full professor, France. Mateo Sonza Reorda, who is with Politecnico di Torino as full professor of the Department of Control and Computer Engineering. He's also the director of the Electronic CAD and Reliability Group and serves as research director of the same institution. And Paolo Rec, who is with Universidad Federal do Rio de Grande do Sul as associate professor. He's currently a visiting professor at Politecnico di Torino, thanks to his Marie Curie Postdoctoral Fellowship Award. We also welcome professors and students of our doctoral program that are with us via Google Meet, and of course, all the people that follow this stream via YouTube. The methodology for this dissertation consists of three stages. First, Luis has 25 minutes to present his proposal. Second, the reviewers participating in this dissertation can ask Luis Ariel questions to confirm that he addresses their suggestions and observations. Later, attendees with a PhD can also take part in this stage. Finally, at the end of the question time, Professor Wilson Javier Pérez and Ernesto Sánchez, as Luis advisors, will have time for brief feedback. Only the first stage will be streamed via YouTube. Now we invite Luis Ariel to start his presentation.
Thank you, teacher Camilo.
The floor is yours. You can start.
Okay, thank you. Okay, hi everyone. Welcome Professors Mateo Sonza, Alberto Bocio, and Paulo Rec. Greeting also to professors and partners of our doctoral program and university. I am Luis Ariel Mesa, and I want to present my doctoral proposal entitled Reliability Assessment of Deep Neural Network Implemented in Parallelized Hardware Platforms. My advisors are Professors Wilson Javier Pérez and Ernesto Sánchez. This work is supported by the Universidad Pedagógica y Tecnológica de Colombia, the doctoral program in engineering, and the Robotics and Automation Research Group. Thank you for your attendance. Welcome. Today's agenda is as follows. Firstly, I want to show you the issue that encouraged this doctoral proposal and some background around the main research focus. Then I will address the state of the art and the problem approach. Also, I will define the objectives and establishing methodology for the execution of the project. And finally, I will present the expected results, the schedule, and the budget. Scenarios like autonomous vehicle navigations, space mission, medical equipment, smart grids, among others, are now as mission-critical applications because they involve risks to life, the environment, and the equipment itself. When this type of application use hardware platforms and digital circuits, special care and attention are required because failures in this operation are not tolerable. Technical aspects and natural phenomena can seriously affect the performance of electronic devices through some natural and technical factors. In this context, aspects as cosmic rays can cause unexpected failures in electronic systems and originate phenomena called single event effects. These events can trigger both destructive and non-destructive effects in electronic chips. The so-called soft errors can be the most difficult to detect and establish potential consequences for many applications. Furthermore, it can cause effects in digital devices that lead to alteration of logical states called bit flips in hardware resources such as the memory, causing a fault. If a fault is triggered, it can propagate to the component output and becomes an error. A system crash occurs when this error spreads out and causes bad behavior of the final outputs. Artificial intelligence, AI, seeks to emulate the cognitive capacity of the human mind. AI integrates various techniques and concepts like fuzzy logic, expert systems, Bayesian networks, data mining, and as artificial neural networks. Artificial neural networks have gained relevance thanks to the incorporation of automated learning in the operation of machines. In this context, deep neural networks, DNNs, have become essential in high-performance electronic applications such as speech recognition and image processing, making them suitable for highly complex applications such as autonomous vehicle navigation. There are crucial aspects for the correct operation of DNNs from the field of the system reliability. Reliability is understood as the ability to tolerate work environment-induced failures, which could lead to system-wide failures. In addition to reliability, digital platforms capable of hosting ENNs have to face application-related challenges such as handling of large volumes of information, processing of complex algorithms, and real-time operation. Although ANNs behave robustly thanks to their high redundancy characteristics in the face of many adverse factors related to the application, recent research shows that this characteristic is not entirely ensured when these networks are implemented on hardware platforms. The literature shows that the reliability problem of DNNs when implemented on hardware platforms can be considered from several aspects: the DNN architecture, the platform software or operating system, the hardware architecture, and finally, the physical aspect. Among the multiple applications found, convolutional neural network CNNs turn out to be one of the most widely used and representative architecture of DNNs. This type of network is characterized by extracting specialized information by executing convolutions in applications such as object detection, video processing, natural language processing, voice recognition, image classification and segmentation, among others. According to work like Scanning 2020, the taxonomy of CNN architecture can be divided into 7 different categories related to this application as shown. Each category presents some specific architectural characteristics at the network level, which allow it to meet its objective. The network architecture of a typical CNN has a hierarchical multi-layer structure that allows for learning through multiple levels of abstraction. The information is subjected to successive convolution operations upon entering the network, extracting from low-level characteristics in the first layers to highly complex features in the last layers. In a CNN, most layers consist of feature maps where each pixel acts as a neuron. Each neuron in a convolutional layer is connecting to feature maps of the previous layer took a significant set of weights. Some of the typical operations of CNNs include convolution operations, nonlinear activation functions, characteristics grouping or subsampling operations, and classification stage made of fully connected layers. The hardware architecture is related to the physical components of a system and their interrelationships. The literature considers the hardware used for the implementation of DNNs in three main categories: analog platforms, digital platforms, and mixed platforms. In this scenario, the implementation of DNNs on digital platform raises challenges related to the hardware architecture that involve aspects such as the processing capacity, energy efficiency, area consumption, accuracy, among others. Digital hardware platform can be viewed from two perspectives. One, software-based devices, and hardware-based devices. In turn, hardware-based platforms are subdivided into programmable logic devices and application-specific integrated circuit ASICs. In implementing applications based on DNNs, platforms that offer high performance are preferred, as the case of FPGAs, GPUs, ASICs, and SOCs. Hardware platform for a given application result in a compromise between efficiency and flexibility. However, different research work showed that parallelized or specialized architecture for applications based on DNNs are much more efficient than the standard microprocessors. Devices such as ASICs, SOCs, GPUs, or FPGAs have been the focus of much of the work in the area, taking advantage of its parallelism, low latency times, and the benefit of some of its specialized functional blocks. Since DNNs require the execution of many mathematical operations, calculations and memory access operations become essential aspects. So the availability and location of blocks such as memory and processing elements are essential for the platform to fit the application better. This figure summarizes some of the most important aspects of the architecture of the hardware platforms most frequently used in implementing DNNs. In the case, we have FPGAs, GPUs, SOCs, and ASICs. The most representative functional characteristics of each architecture are highlighted, while on the other hand, the respective vulnerabilities to impacts from high energy particles and other phenomena are shown. The vulnerabilities presented by the different platforms in resources such as memory and processing elements are especially highlighted. The literature review indicates that data representation is another crucial factor to analyze within the functioning and reliability of neural networks. Data representation is related to factors such as the DNN operation, the disturbance magnitude, the hardware platform utilizations, and the management of information within the application. The magnitude of the disturbance introduced by a phenomenon such as an issue in information bit within an application will depend on the data format and the location of the disturbed bit within the encoded information. On the other hand, the data format can affect the number or complexity of the functional blocks used during the implementation and intervene in using the platform hardware and handling the information. This slide presents illustration of two papers that face the effect of data representations on the behavior of deep neural network as shown here. Among the most used tools to estimate the reliability of a digital system are fault injector methodologies. These tools allow the intentional introduction of specific faults or errors in functional blocks to analyze their behavior, such as memory or processing units. The fault model considers the type of fault to be injected, the moment in which the injection must be carried out, and the part of the system that need to be attacked. Various work have been executed that propose different schemes to perform application-specific block fold injection, as shown in the conceptual scheme in the figure. Other aspect intervening the reliability that a DNN implemented in hardware platform can present, such as masking and reliability improvement techniques. Masking can positively affect the reliability and increase the robustness of ANNs. However, some of these mechanisms, such as electrical and temporary, are less effective because the transistor in semiconductor devices scale more and more. Reliability improvement techniques are especially based on selective hardening techniques. In contrast, traditional hardening can increase surface and energy consumption for a given application. For a DNN, given its considerable size, hardening techniques may not be feasible given the limited resources for specific hardware platforms. To validate the reliability assessment, the planning and execution of the experiment must involve different components to improve observability and controllability. In this way, it's necessary to contemplate metrics that involve the neural network architecture, seeking to decompose it into current models in terms of the high levels of abstraction with what is available for the case. For hardware, the metric must consider the type of architecture of the device, trying to distribute the application in layers and functional blocks. On a specialized architecture, platform architecture emulation may be required. Finally, the test requires a set of stimuli that ensure that the majority of the functional blocks and structures are affected. The methodological literature review procedure followed for the development of the proposal involved the use of scientific databases and search engines, applying different time windows, especially within the last 5 years. The search question focused on 3 strategic aspects. 1, identify trends in the implementation of DNNs on platforms and hardware. 2, determine the reliability of neural network implemented on hardware platforms. And 3, identify research opportunities in reliability assessment of DNNs. The result led to the identification that although many studies carry out the hardware implementation of the DNNs, not all of them address the reliability aspect. The results showed that platforms such as FPGAs, GPUs, ASICs, and SOCs are the most easy to implement DNNs and the ones that are currently the most worked. Specifically on the issue of DNN reliability assessment, many works have been found from general aspects about the implementations on hardware platforms. The most relevant results are shown here. In this sense, a growing trend was identified regarding the reliability assessment for these data platforms types. Various studies have been made to organize hardware and network architecture to inject faults and evaluate reliability. In Ruospo's work et al. In 2020, a pipeline-like multi-level structure is used managing level of abstraction, application, and synchronization. Desayu's work et al. In 2020 proposed an FPGA-based platform to emulate faults in the architecture of a DNN, imitating faults that affect hardware. The bibliographic review shows great efforts to propose the methodologies and approaches that facilitate the reliability assessment of DNNs. Many of these works are based on frameworks that carry out fault injection campaigns at the simulation, emulation, or physical level. In this context, opportunities were identified to contribute in the area when considering the evaluation of the reliability of the DNNs implemented on hardware platforms. This process took account the DNN architecture, the hardware architecture, and the data representation as a reference. The present proposal intends for the case to address CNNs or other emerging typologies implemented in highly parallelized platforms such as FPGAs, MPSOCs, and optionally GPUs, while considering different data representations. Once this small gap was identified, the third question that arose was the following one: how to evaluate the reliability of a DNN implemented on highly parallelized digital hardware platforms, considering the neural network architecture, hardware architecture, and data representation. And the respective hypothesis generated will be the evaluation of the reliability of DNNs implemented in highly parallelized digital hardware platforms, considering their network architecture, hardware architecture, and the data representation, will contribute to the identification of possible vulnerabilities of this type of neural network, which allow ensuring their correct operation and expanding knowledge in this area. The general objective is developing an approach to evaluate the reliability of DNNs implemented on highly parallelized digital hardware platforms. And the specific objectives are: 1. Identify the factors that affect the reliability of DNNs implemented in highly parallelized digital hardware platforms, considering its network architecture, hardware architecture, and data representation. 2. Designing an approach for evaluating the reliability of DNNs implemented on highly parallelized digital hardware platforms. 3. Developing and implementing an experimental setup for the proposed approach. Finally, evaluating and validating the proposed approach effectiveness under the experimental setup restrictions. The methodology proposed for the fulfillment of those specific objectives comprise 5 strategic stages: reliability characterization, approach design, experimental setup design, approach implementation, and validation. The first stage aims to obtain a characterization of the factor affecting the reliability of the DNNs. The result is essential for the second stage to carry out the design of the reliability assessment approach for DNNs. The third stage will focus on developing the setup for validating the design and approach application based on DNNs. Finally, the fourth and fifth stage will be based on starting the experiments, collecting the necessary information, and validating the proposed approach. The most important stage of the project methodology established for the project will be described as follows. The first stage identifies the factors that affect the reliability of DNN-based application when aspects such as network architecture, hardware architecture, and data representation as considered. Preliminary assessment tests will be carried out for the case using updated scientific information, specialized software and hardware development platforms, some technical training activities in digital design and artificial intelligence have already been carried out. In addition, it's expected to obtain a specification for the construction of the reliability evaluation approach. The second stage aims to develop the approach proposed by the work. In addition to the results obtained in the previous stage, it's necessary to consider the identification and selection of the fault models, the techniques and methodologies defined to reliability assessment of the digital systems, and the DNN's abstraction models. The application of these techniques involve testing sensitive hardware components such as memory, arithmetic blocks, and peripherals, etc. The third stage consists of developing a configuration to validate the proposed approach. In this scenario, it's necessary to identify the selection of representative inputs, the setup specifications, the coverage metrics, and the tools to improve the observability and controllability in the fall injection process. In addition to experimental work resources already mentioned, some laboratory equipment will be used to verify the basic operation conditions of the hardware platforms. A preliminary test approach will also be obtaining for the reliability assessment of DNNs implemented in hardware platforms. The expected results for the execution of the project are considered from two perspectives: research results and academic results. Research results are based mainly on determining, first, the proposed approach and the aspect related to the reliability of application based on DNNs, considering the three mentioned variables. And second, experimental tools to evaluate and validate approach based on the reliability of DNNs. For academic results, participation in events, publication of works, visiting research groups in the area, and strengthening research process in the JIRA group stand out. The project schedule is made up of 30 months, in which is intended for execution each of the 5 stages formulated in the methodology. Also, there are other activities related to the dissemination activities and the links strengthening with the specialized scientific community, the progress reports, the doctoral internship, the submit journal papers, and the doctoral dissertation. The estimated budget for the execution of the doctoral project established 5 aspects related to the software, the hardware, the laboratory equipment and experimental setup implementation, and the search and socialization of results. The costs are divided into resources provided by the Uptc, the research group, and the doctoral student. The total cost is estimated to be close to $63,900. Thank you very much for your attention.
No, thank you, Luis Ariel, for your presentation. Now we're gonna close the streaming on YouTube. So these are like the last words. So on behalf of the doctoral program in engineering and the electronics engineering graduate school, we thank everyone who followed this presentation via YouTube. We hope that you have enjoyed this event and that its content has been meaningful to you. So thank you very much once again.